All right. So, as far as the exam goes, we've got an answer key posted on Google as well. But if you've got questions about things, come by the meeting. I'm happy to go over things always. I want to mention that you are going to have a quiz that's due tomorrow night on Moodle. So the reason why I put this particular problem back up on the board, we went through this last Wednesday, I believe it was. This is basically the type of problem I'm going to ask you to do on the quiz on Moodle. Okay, literally just like this. So you've got a polynomial that you're given one of the complex zeros, and it asks you to find the rest of them. Okay, so in the quiz, I just want to mention how you want to type things in. So one of the things it's going to ask you to do is start with the complex zero and go through it first. And then it's going to ask you what are the coefficients when you get done with your first line, excluding that zero. So what it's asking for are these numbers here on the line. It's going to ask you to put commas in to separate them and no spaces. If you put spaces in there, Moodle is going to count it wrong. It's going to try to auto grade it as it goes. Okay, but literally just that one problem, just like this one. Okay. So that'll be due tomorrow night by midnight. It has a 45-minute time limit on it. Again, it's just the one problem, so it's got several parts to it. But again, when it's asking you for different answers, especially when it's asking you for the result of the synthetic division, it just wants those numbers when you get done, without the final zero. Any questions about anything? Yes, go ahead. Yeah, so the first part will be do the first step of the complex zero, then ask for another step, then ask for rational zeros. Kind of put all these things together. Other questions at all? Ooh, sweet. All right, well, let's start some new stuff then. And that's what the new handout's about. So we've spent a good deal of time talking about, a particular type of function, which are those polynomial functions. So we want to start building up our database, if you will, of different types of functions and what different properties they have as we go forward. So your polynomials are really, really nice functions. They're exceptionally useful functions. They're used to, even later on down the road in other math classes, used to help you approximate other types of functions that aren't so nice. Right? So polynomials are exceptionally useful, and we've gone through and analyzed as much as we can until we get more machinery. We've analyzed as much as we can polynomial functions. So in this end of this chapter and in the end of the next chapter, we're going to talk about a couple of different types of functions, also useful, but maybe not necessarily as nice as polynomials, but not too bad. So the first ones that we're going to talk about are rational functions. The root word of rational is ratio, this part. We've already talked about rational roots, right? We made fractions. So rational functions are fractions, okay? So what types of fractions are they? So we can write the rational function as p of x over q of x. So it must be a fraction of something. But what's it a fraction of? What are these functions that we have in the numerator and the denominator? Well, those happen to be polynomials. Okay. So the numerator is a polynomial, the denominator is a polynomial. We already know that polynomials are really, really nice functions. In particular, are there any values of x that you cannot plug into a polynomial? Or can you plug anything you want into a polynomial? anything, right? Remember, polynomials are just x's to positive integer powers, right? You don't have any roots, you don't have any divisions, right? And then you have multiply a number by the x's and then add those things all together. That's what a polynomial is. So we have no domain issues when we talk about polynomials. When we start introducing ratios, though, what might go wrong? The zero in the denominator, right? And so that's exactly what we need to pay attention to. It's the values of x. We need to worry about the values of x that make that denominator, which I've labeled as q of x, equal to 0. And we've already seen this, right? We've already worried about domain problems before for functions that we've labeled. We're really interested in when the denominator is equal to 0, right? When the denominator is equal to 0, that means that we've got, we're trying to divide by 0, which causes all sorts of issues. So those are the values we need to worry about. And so what we're going to be interested in a lot today is what happens near those values, or what happens at those values where we're putting in zeros in the denominator. So to do a very, very simple example of what happens when we put zeros in the denominator, let's look at this y equals 1 over x function. What's the bad number to plug in for x? 0, right? With 1 over x, putting 0 in for x is going to cause an issue. All right. So what we're interested in is what happens around that x equal to 0 point. So to get it, we've already talked about what the graph of this looks like, but just to remind, if we just pick in some points for x, let's start with a few here. I can't plug in 0, but let's just start in with some integers here. If you put in -3, what do we get out? -1/3. Put in -2, you get -1/2. Put in -1, we get -1, right? We're just doing reciprocals, right? So on the other side, we'll have 1 and 1/2 and 1/3. In particular, notice that the bigger the x gets, the smaller the y gets, right? If you divide by bigger and bigger numbers, you get smaller and smaller numbers. That doesn't tell me a lot about what happened at 0, so let's put in a few other numbers and see if we can figure out what happens kind of near the 0. Let's say we wanted to put in things like -1/2, maybe -1/10, -100th, and do the same thing on the other side, just without the negative signs. Again, I'm just picking numbers, right? There's nothing special about these things. I just want them to be close to 0. If we plug in -1/2, well, again, the function says flip it over. So if you put in -1/2 in for x, what do you get out? -2. And if we put in +1/2, we get out 2, right? If you put in -1/10, what do you get out? -10, right? Because again, the function is take the reciprocal, right? 1 over 1/10 is 10. So we get -10 there. We get +10 if we put in +1/10. What about when you put in -100th? -100, right? And the same thing, we get +100. So what's happening here? I'm putting in that really, really, really small numbers and dividing by them. What's happening? I'm getting things that are getting really big, right? So if you put in 1,000th, you get out 1,000, right? If you put in 1,000,000th, you get out 1,000,000, right? So the closer our x's are getting, our y's are getting really, 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 really big. And we've already seen, like I mentioned before, we've already seen the graph of 1 over x.
But just to sketch it again here, we said when we put in 1, we got out 1, put in 2, we got out a half, put in 3, we got out a third, and so on. On the other side, we get something similar, just on the negative side of things. But now when we put in a half, we got 2. When you put in a tenth, which would be close to the x-axis, or excuse me, close to the y-axis, we'd be getting out 10. Likewise, on the other side, we're getting really, really big things. And so we're getting a graph that looks like so. I missed my points, but you get a graph that looks like this.
So something interesting is happening here, that we're getting this vertical line, the y-axis in particular here. We're getting this vertical line that our graph gets really, really close to. So in this case, we refer to that the line x equal to 0.
We refer to that as a vertical asymptote.
It's a vertical line that the graph of the function approaches. Vertical asymptotes can tell us interesting things about the function. Right? It helps us. Remember with all the stuff in the polynomials, we looked at where it crossed the x-axis, looked at its multiplicities to determine if it flattened or not, crossed or not. Right? Figure out the y-intercept with the end behavior to get us a graph. We're going to do similar things with rational functions. One of the things we're going to look at to help us get a graph are vertical asymptotes. This okay so far?
So let's look at the next one, where it asks for all the vertical asymptotes of f of x equals x plus 3 over x minus 2.
Well, in the previous example, what did we notice went hand in hand with the vertical asymptote? Well, in vertical asymptote at x equal to 0, what was wrong with x equal to 0? Yeah, putting it in the denominator makes the denominator equal to 0, right? Trying to divide by the 0. So if you were looking at this particular function, where might you guess there's a vertical asymptote? At 2, right? So right away we notice that our domain
would be negative infinity to 2 and 2 to infinity. So we already know there's a problem at 2 of some sort, right?
And we can check this numerically to see whether or not we have an asymptote. And this is going to be important for the next example. We can check this numerically if we want to make sure that we actually have an asymptote.
So for example, if I put in maybe 2.1, if we put x equal to 2.1 in here, so what do I get out when I do f of 2.1? I would have 2.1 plus 3 over 2.1 minus 2. 2.1 is pretty close to 0, right? Or not, pretty close to 2, not 0. We would get 5.1 on top and 0.1 on bottom. I purposely picked this one because that's a tenth. If I'm dividing by a tenth, what am I really doing? Dividing by a tenth is the same thing as multiplying by what? 10, right? Remember when you divide by a fraction, you multiply by the reciprocal? So if I'm dividing by a tenth, I'm really multiplying by 10. This turns out to be 51, right? If you put something in like 2.01, and again, the only reason why I'm doing this, we're not going to do this every single time, but I'm just trying to illustrate what's going on here at 2 in particular. If you put something in like 2.01, on top we get 5.01. On bottom we get 0.01, which is the same thing as 100th, right? dividing by 100th is really multiplying by 100, right? And then we end up with 501. Doesn't it look like those outputs are getting really, really big? Yeah. So in this case, we would say that our vertical asymptote would be x equal to 2. And that's the only place we're going to get a vertical asymptote, because everywhere else, I can plug the number in for x and get out a y, right? Vertical asymptotes are going to pop up when you get the rational function being undefined. Everybody okay with this so far? All right. Now looking at the next one, where do we notice we have a domain issue? At -3, right? Oops. So if I look at the domain here, it would be -infinity to -3 to negative and union -3 to infinity. You might be tempted to say, hey, I bet there's a vertical asymptote at -3, x equal to -3, right? That's what's happened in the previous two examples, isn't it? We put in x equal to 0. We had a problem in the 1 over x, and we noticed that we had a vertical asymptote. Notice we also had a vertical asymptote here when we put in, had x equal to 2. However, let's look at this particular function. Can you factor the numerator? Yeah, what does it factor as? Yeah. Notice your numerator here factors as x minus 2 times x plus 3. What can we do now? Yeah, they cancel out the x plus 3s, right? The x plus 3s would go away. And we would just get x minus 2, so long as x is not equal to -3. I cannot do this cancellation if x is equal to -3, right? The reason why, can I plug in -3 over here on the right? Is it okay to plug in -3 here? Yes. Is it okay to plug in -3 here? No. So these two things are not equal when x is equal to -3. Okay. However, this does help us determine whether or not we're actually going to get a vertical asymptote. Notice that even if I make the denominator really, really small, I have the exact same thing on the numerator, right? And those numbers would just cancel out. We agree? Okay. So even if this is 0.0001, I'd have a 0.0001 in the numerator, and those would just go away. Right? So notice that we actually, what we get on this particular thing for a graph would be a hole. If you just look at y equals x minus 2, what kind of a graph does that have? What kind of a graph is that? It's a line, slope 1, y-intercept of -2. Right? So if we want to graph this function, I have to make it a little bit smaller because I didn't leave myself a lot of room here. So you'd have a y-intercept of 2 and a slope of 1. So your line looks like this, except that when you get to -3, you should get -5, right? There's going to be a hole there. It's going to look like this. The reason why we have the hole is because, again, we can't put in -3. But everywhere else, it looks like a line, doesn't it? It looks like x minus 2. So is there a vertical asymptote on this graph? Does it look like? No, there's not a vertical asymptote on this one. So there are no vertical asymptotes for this one. There's a hole at x equal to -3. All right, so what happened differently in this example than in the previous example? Zoom out just a little bit so I can try to see both of them at the same time. What's the difference between example 1, where we had an asymptote, and example 2 here where we did not? Sorry, we're both at the same time. Sorry. What was it?
We didn't have it in fraction. For the second one, it's not in fraction.
Okay, so yeah, so what happened for that second one? It canceled out, right? Is that what you were saying? Yeah, so we had the polynomial on top that we could factor and we canceled it, right? Notice that the problem in the denominator canceled out with something in the numerator. Okay? So if you get a common factor on top and bottom and cancel it out, there might be a hole there instead, right? Rather than an asymptote. So let's see if we can apply that to the next one. Work on this one for a second and see if you can figure out where the vertical asymptotes are versus the holes. What do you think we should do first? Yeah, factor everything we can, right? Let's do that first. What do you get when you factor the top? What is it? X minus 5 and x plus 1, and on bottom. Good. Okay. That's what you should do first. Anytime you're being asked to find vertical asymptotes, factor everything you can. Factor the numerator, factor the denominator. In particular, we need to know where the denominator is equal to 0 to see where we have any potential vertical asymptotes, right? Because domain issues and vertical asymptotes go hand in hand, and you already know to check for domain, set the denominator equal to 0, right? So where are your domain issues? Yeah, 4 and 1, right? Okay, so we know that the domain, I'll write that off to the side here, will be negative infinity to 1, 1 to 4, 4 to infinity. Okay, do that first. So your potential candidates for vertical asymptotes are x equal to 1 and x equal to 4. Did you have any same issues like we had in the previous example? No, nothing canceled, right? So again, even if something in the denominator gets really, really small, the numerator is not really, really small at the same time. There's no canceling going on, right? So we're going to end up with vertical asymptotes at both of those numbers, okay? So your vertical asymptotes then will be what? We have x equal to 1 and x equal to 4, right? Asymptotes are lines. Lines are described by equations. Don't just write 1 and 4. Numbers are not equations, okay? The proper form for a vertical line is x equal to, the equation of a vertical line is x equal to a number. So make sure you write x equal to 1, x equal to 4. What if instead of having a minus 4x on top, we would have had a function that looked like x squared plus 4x minus 5? Yeah, so notice in this case, you would have had x plus 5, x minus 1, right? It would have factored kind of the other way, if you will, right? These two functions have the exact same domain, right? I still cannot plug in 1 and I still cannot plug in 4, right? They have the exact same domain, but in this case, the x minus 1s go away as long as your x is not equal to 1, right? So on this one, what would you say the vertical asymptote is? Just 4. Good. There would be a hole at x equal to 1, just like what we had in that other example. There'd be a hole, but no asymptote at 1. Does that make sense? So, moral of the story, when you're looking for vertical asymptotes, put your rational function in lowest terms. See if there's any common factors that factor out before answering the question. Questions on that at all? So we've seen vertical asymptotes. Let's go back to that very, very first example we did before we do the next one. Because there's something else going on with that first example. We already said it a little bit ago. As your x's get bigger and bigger, what happens to your y's in this first example? They get very small, right? So, for example, if x is 10, you get 1/10,000. If x is 100, you get 1/100,000. And your graph is going to get really, 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 really close to the x-axis, right? That's what we refer to as a horizontal asymptote. Okay? Same concept, right? We're getting really, really, really close to this line, right? It approaches that line, it gets really, really flat. That's what we mean by a horizontal asymptote. Okay? So let's see if we can apply that same thing over here. All right, so let's see what happens. No matter what you plug in for x, what's the numerator always going to be? 1, right? No matter what you plug in for x, the numerator is always going to be 1, right? Okay. So as x gets really, really big, what do you expect to happen to the fraction? If your numerator is always 1, and you divide by bigger and bigger and bigger and bigger numbers, what do you expect to happen? It gets smaller and smaller, right? They're going to get closer and closer to 0 for the outputs, right? To put in some things specifically, we start graphing things here. First, can you tell me where there's a vertical asymptote? Now, x equal to 1, right? Notice that 1 makes your denominator 0, and certainly we did not cancel out an x minus 1, right? Typically, on a graph, when we denote an asymptote, we'll use a dashed line. The dashed line is not part of the graph, okay? The dashed line is just there to help us draw the graph, okay? If you graph one of these on your graphing calculator, a lot of times your graphing calculator will insert a line there. The reason why is because your calculator just plays connected dots. It just plots a bunch of pixels and tries to connect them together with lines, okay? Unless it actually specifically tries to plug in 1 into your calculator, it's going to take 1 at the top and connect to 1 at the bottom. It's going to look like it's part of the graph. So anytime, if you do have a graphing calculator you're plugging these into, note that if you're near a vertical asymptote, it's going to put something in your graph that's not supposed to be there. In any event, that's our vertical asymptote. Pardon me. Let's just start plugging some numbers in rather than making a table. If we put in 2 for x, we get 1 in the denominator, so we just get 1 out, right? If we put 3 in the denominator, we get 2, or 3 in for x, we get 2 in the denominator, so we get a half. And then we'll get a third and a fourth, just like we did in that previous example. So we're going to get something that looks like this when we draw it. Eventually, we're going to get away from plugging in points and just start sketching the graph. Notice that I had to go up, right? I had to go this way. I couldn't turn around and go this way. Because if I turned around and went this way, I'd be crossing the x-axis, and there aren't any zeros here, right? I didn't get 0 out of it. So I had to go up. What about on the other side? What do you get when you put in 0 for x? -1, right? We're down here. And then likewise, you'll get points that come closer this way. And so we get a graph that looks like this. And same principle, I can't go up because we didn't cross the x-axis. So notice that your graph is getting closer and closer to the x-axis as x gets really, really big. So we have a horizontal asymptote of y equals 0. It's the x-axis in this case. Is this okay so far? Okay. So, pardon me. In this example, as x got really, really big, the numerator was always 1. The denominator got really big and made it really small, right? So we know that we were getting closer and closer to 0. Now in this one, as x gets really, really big, both the numerator and the denominator equal 0. Get really, really big, right? So I can't do that same type of analysis that we did up there because both are getting really, really big at the same time, okay? However, we can play with this a little bit. We could do a little bit of long division. I'm not going to do that right now. I'm just going to do something a little bit easier. Pardon me. I'm going to write this as tried and true trick in math is to write 0 cleverly. I could do polynomial long division and you'd get the same answer, but a tried and true trick in math is to add and subtract the same thing. Adds 0, keeps everything equal. Now let's split this fraction right here. By the way, you're not going to have to do this every time. I'm just going to show you what's going on.
So I split my fraction right here at this plus sign. Why did I split it there? What can I do with this first fraction now that I have written?
Yeah, it becomes 1, doesn't it?
We okay with that so far? Okay. Again, we're trying to get at this by looking at what happens as x gets large. You're not gonna have to do this every single time. We're gonna have a rule that tells us what we get. Okay. All right. But I just want to show you what happens in this case. All right. Let's ignore the plus 1. What did we say happens to that fraction that's to the right of my hand? What happens to that as x gets really, really big? Either in the positive or the negative direction. What happens? It gets really, really close to 0, right? And then we add 1. So what's going to happen is you get the x gets really, really big. The outputs are going to get really, really close to 1. Because we're going to take something really, really close to 0 and add 1 to it, right? Okay. So
What happens here, and we can actually see this from a transformation standpoint as well, we still have that vertical asymptote at 1. But now, this was the exact function we graphed before, the one I just circled, isn't it? What does the plus 1 do to that graph? It shifts everything up 1, right? Doesn't it? Yeah. So we're going to have a horizontal asymptote here at y equal to 1, and you're going to have a similar looking graph. It's going to go this way and this way. So this one's going to have a horizontal asymptote of y equals 1. So far, so good? Yes.
So how's that the horizontal asymptote to one above it? So it's the same equation.
that's not quite the same equation, right? We're taking the same thing and we're adding 1 to it. So it's getting everything's getting shifted. Yeah.
So far, so good? Let's do this next one. I can be equally as clever like we just did in the previous. Like I said, we're not going to do this every single time, I promise. I'm going to do the exact same thing I did in the previous one. Let's add and subtract 1. And split it at the plus sign. Let's look at that first fraction. What can you do with the x squared minus 1? Difference of squares, right? And then what happens? Yeah, the x minus 1s go away again, right? Right.
So I can rewrite this x squared over x minus 1 as x plus 1 plus 1 over x minus 1. All right. Same idea now. Let's analyze what's going on. We cover this part up. What happens here as x gets really, really big? What did that piece go to? It gets really, really small. It goes to 0, right? Okay? Now, but remember, we're thinking about as x gets really, really large, right? As x gets really, really large, what's x plus 1 going to do? Get really, really big, right? If I take something really, really big and add 0 to it, it's going to get big, right? Big plus 0 is still big, right? Okay? So is this going to get closer and closer to a number? If I just said as x gets really, really big, the whole thing gets really big, is that going to get closer to a specific number? No. Okay. So this one's not going to have a horizontal asymptote. Now it does have a special type of asymptote that we'll talk about later. No horizontal asymptote. It still has a vertical one.
Forgot the word horizontal in there. Let's look at what happened of the forms of the function to see what is actually going on here. So scroll back up to the top. We had just a constant on top and an x on bottom. Well, the degree of the bottom here, the highest power of x we see is 1. What's the highest power of x we see on the top? 0, right? Because we like it understood x to the 0. So notice I got x to the 0 essentially on top and x to the first on bottom. What about the next example? What were the degrees of the top and the bottom? Yeah, it's like x to the first, it's the first degree and first degree, right? And the third one? Yeah, second and first, right? So notice in the first example, the degree of the top was less than the bottom. Second example, they were equal. Third example, the top was bigger for degree, right? All right. So let's see if we can make a guess at what the next answer should be just by doing that same type of analysis. And then we're going to come up with a general rule, okay? What's the degree of the top? The first power, right? So 1, right? Degree of the bottom? 2, right? So which is bigger, 1 or 2? 2. So the degree of the bottom is bigger. So of those 3 options, which one do you think this is most like? First, second, or third? The first, right? What was the horizontal asymptote in that first one? 0. So what would you guess the horizontal asymptote here is? 0 as well, yeah. Y equals 0, and again, the reason here is that the degree of the top, the degree of the numerator, is less than the degree of the denominator. We'll go through and talk about more specifically why. But it's going to behave like that first example. How about the next one? What do you think is going to... What's the degree of the top in the next one? It's a 3, right? And on bottom, 1. So the degree of the top is bigger. So what this is going to be more like example 1, 2, or 3, do you think? 3, right? And in that case, what did we say the horizontal asymptote was? There wasn't one, right? So no horizontal asymptote. Degree of the numerator is greater than the degree of the denominator. Now let's think about this for a second about why that might be true. When we talked about end behavior for polynomials, what did we worry about for end behavior of polynomials? When we were looking at what happens as x gets big, either in the positive or the negative direction for end behavior, what term did we worry about? The leading coefficient, that leading highest power, right? The leading term, correct? Well, finding horizontal asymptotes is just like doing end behavior, but for a rational function, right? So if I look up here, this first one, I'd be just looking at those two pieces, right? If I'm thinking about end behavior, it's the highest degree term that matters. What I just circled up there, what would that simplify to? 1 over x, which we said had a horizontal asymptote of 0, right? Y equals 0. Over here are your leading terms. If I just simplify those, what would you get? X squared. That looks like this, doesn't it? No horizontal asymptote there, right? Okay. All right, so let's look at this one. What two things do you for horizontal asymptotes? What two things do you think you should concentrate on? Yeah, the highest degree term in the top and the highest degree term in the bottom, right? If you just look at those two terms, what would that simplify to? If I just look at these two terms, that simplifies to 2, right? So what would you think the horizontal asymptote is then? Yeah. And specifically, since it's a horizontal line, we should write y equals 2. Good. And in this case, the degree of the top, the degree of the numerator, equals the degree of the denominator. So we looked at the 2x squared over x squared, which was just 2. Look at the leading terms again. So we'll recap this next time since we got about 1 minute left. Okay. So this is exactly what we're going to look at. For when you're looking at horizontal asymptotes, we don't need to worry about that fancy rewriting that I was doing at the beginning. We just need to look at what's going on with the degree of the top and the degree of the bottom. So we'll recap that out, and we'll have another type of asymptote we'll talk about, and then we'll do more examples next time. Right. Don't forget, your Moodle quiz is due by midnight tomorrow, or 11:59 tomorrow night. Okay? Have a good one. We'll see you on Wednesday, if not before.